So hi everyone, thanks for coming. My name is Stefanus. I work for a company called Thalmic Labs. We build this right here. This is a myo. The myo is a device that reads the electricity moving along your arm as you are using your muscles, so that it can be used to control various devices with kind of gestures and so forth. So today's the first time I'm actually going to be using one of these at an external presentation. So I am both excited and mostly terrified. But bear with me if things go awry. We'll blame it on the Bluetooth connection. If you can all agree, then that's good. All right, so I'm going to be talking today about something called Hourglass interfaces for C++ APIs. I'll explain what those are in a little bit. Just so you know, a bit of background, I have escaped the standards committee. I was on there for about 5 years, most recently as project editor for C++ 14. That does not make me an expert in anything in the standard. But I am a practicing programmer, write a lot of library code in my day-to-day activities, and kind of going to be talking about some ways to make writing shared libraries a little saner. All right, so let's see if this works. Here we go. There we go. All right, so we'll start off with a little bit of motivation and an introduction. I'm going to talk about some best practices as well, and show you lots of code. So shared libraries, they're things. They are boxes containing code and data, and they have interfaces. And typically we think of the interface of a shared library, which is kind of its entry points and all the exposed data that it might have, all of its symbols, as something belonging to that library. But when you link with a shared library and you use it, what you're really doing is putting the interface that that library exposes at the time into your program as well. It could be a program executable, or it could be another library, whichever case. So you have this contract between the shared library and the client that's using it, and the client is going to make all kinds of assumptions that when it calls a function in the shared library, for example, that it has certain parameter types and numbers of parameters, that data that it knows about, data types like structures out of that shared library have specific fields in specific places, and so forth. So there's all these kind of assumptions that are now baked in, not only into the library, but into your client program as well. It gets worse than that, because there's also a couple other things that kind of get pulled in as a side effect of this. One is the ABI, right? This is your application binary interface. It's essentially a specification of how do you call functions, how do you pass parameters to functions, how do you lay out things, how do you mangle names, etc. And because that has an impact on all of these little implicit contracts, it kind of gets baked into your usage as well. And then there's common libraries. So if your interface uses, for example, the std_string class, and your library was built with a particular implementation of std_string, then your code on the other side had better use the same implementation of std_string as well, or at least a binary compatible one. Otherwise, things are going to get messy very quickly. So the point here is when you're calling into a library, you're not just calling into that library. You're really baking in all of these assumptions about that library's interface into your client code. And so because of that, you want these things to be consistent. You don't want them to sort of change too much, because otherwise you can't substitute in a new library anymore. So if you have different ABIs, for example, if you do end up linking code that uses one ABI into code that uses another, and some part of that interface depends on a part of that ABI, you can get some pretty terrible, subtle problems occurring. And some of you have probably encountered this. So I'm going to just briefly relate something that happened to me about 6 months ago. I was using a library. The library provided class A. This was a graphics interface library, basically a GUI library. And in our application, we needed to do something a little different with this one control that displayed animated images, like GIFs or videos, basically. And did the work. We inherited from it so that we could override some virtual function that we actually needed to override as part of what it was doing. That all seemed hunky-dory, and committed the code. We tested it, at least somewhat. It worked on my Mac, so that's got to be good enough, right? And then a little bit later, we discovered, on another operating system, on Windows, it never plays the animation. And that's unfortunate. It's unfortunate that the bug was it never plays the animation, not it crashed, because we had to kind of find the part of the code that was responsible for playing the animation, which is all in the library client code, which we luckily had, and step through it and see what's going wrong. And after about 2 days of pretty much tearing my hair out, stepping through various things, the problem wouldn't reproduce in debug mode, which is major pain in the ass. Pardon my French. We just started seeing some really strange things, like the this pointer not pointing to where it's supposed to, which is not a good sign. Now I already gave a hint as to what was actually wrong, and I should have clicked them right away rather than a day later. The problem was the client, the library was built for debug and with various compiler settings that are involved in that. We were built in release, and of course I could only reproduce the problem in release. And it turns out, the compiler laid out classes a little differently, and so where the release build thought certain data members of the class wasn't where they actually were, because presumably some padding for debugging or something like that got inserted. So that was 2 days wasted effort for me. It wasn't like the worst bug I've ever encountered, but it's one of those where you just get angry. And I do a lot of library work, and my goal generally for libraries is I want to get out of the client's way. The last thing I want is for somebody, they want to integrate this with their application, a game, or a video player, or presentation software, whatever it is, and they're linking in my library, and now suddenly they have a bug where something behaves badly. That's not good. So in particular, things I'd like to make sure are the case is I don't want my clients to have to build my code if they don't want to. I don't mind giving them source code most of the time, but I rather not just give them a tarball and say, there you go, we managed to build it here. I'm sure you can manage to build it too. How hard is building, right? Like, nobody ever has trouble with that. So I'd rather be able to give them binaries, which means, I could maybe try and do something headers only, but again, that's not always an option for a variety of reasons, including compile time. I don't want to have to make my clients change how they build their code. Of course, they're going to have to make some changes just to pull in my library, but that should be it, right? It shouldn't be, oh, please pull in my library, but also please turn on exceptions and RTTI, and by the way, it doesn't work in release mode, so you're going to have to just build the bug from here on out. I hope that's okay. Not so great. I really, really don't want them to have to rebuild their code because I shipped a fix, right? So customer is out there, they have code shipping using my library. It's very exciting. And they find that for people with whatever green laptops, it fails, and we find the bug. We fix it entirely within our own library, and we give them the library, and now they have to go and make recompile because there was some change to a class that I defined, which is now a different size, even though the interface hasn't changed at all. The binary interface has. I want to avoid those things. I really want to be able to just, assuming my real interface hasn't changed, I want to be able to just give them a new DLL, a new dylib, a new .so, and just have them be on their way. Ideally, they should even be able to tell their users, just drop this magic file over here and everything will get better. And then last but not least, I rather not have them learn a new language if they don't want to. You know, if my library is in C++, and they are Python or JavaScript programmers, they're people too, it's okay. You know, if they want to learn C++, great, but probably the instructions for my library shouldn't say step 1, learn C++. You know, not great. So I'd like to be able to support different environments, different languages. Okay, so that's where this hourglass pattern comes in. So why is it called hourglass? Simply because of the shape. So an hourglass is kind of fat on the top, fat at the bottom, thin in the middle. So we'll abstract that away. And what we do in the hourglass pattern is actually very simple. We take a bog standard C++ implementation that have all kinds of cool things in it and code, and you know, maybe it uses lots of OO, or maybe it's all templates, or whatever the case may be. We wrap that in a thin C89 API, not C99 or C11 or something like that, C89, the good old classic. And we stick on top of that a nice C++ interface so that my clients don't have to use C. And potentially we might stick other interfaces on there as well. And specifically, the interface we build on top of it is headers only, or at the very least, that one does, you know, deliver the source code or ship a static library or something like that. But it's separate. It's not. It doesn't, you know, kind of bring in its own shared library. It just talks to that API. Pretty simple idea. Maybe seems a little odd to do this. You know, why would you? But we'll get into that. So some of the reasons why this is not a crazy idea. First of all, it avoids a lot of ABI-related binary compatibility issues. If you pick the right sort of subset of C89, you can essentially be guaranteed that release build, debug build, this version of the runtime, that version of the runtime, all that stuff, you know, it's not going to make a difference. Of course, it doesn't make a difference because you're avoiding using that stuff, but if you ever review other people's code, you know that like saying that you can avoid something is not quite as good as actually like being forced to avoid something sometimes. So, you know, forcing yourself to use this subset of C really helps get rid of a lot of that. The C ABI is super stable, right? On pretty much any major platform out there, it really doesn't change much or at all, at least not for the parts that we're going to use. So it also, like I said, it enforces use of non-trivial C++ types, which just cuts down on dependencies on things like, you know, which version of the standard library did you compile this with, and so forth. That doesn't mean you don't get to use std_string still. You can still use it in your big, broad interface at the top. You can still use it as much as you want for the implementation. It just means data doesn't flow via std_string from one executable into the other. As you'll see, side effect of following this pattern is keeping the internal layout of all your data types a secret, so it's completely opaque. It's all hidden away. If you add let's say, you know, you find that, oh, this class should have actually been locked for some of its operations, so we're going to add a mutex to it. Well, now the class is a different size. Maybe the mutex is in the middle. Things aren't quite where they used to be anymore. Stuff like that, you just don't worry about. You go wild in your own code base. You make whatever changes you like, and you never have to worry, oh boy, was that one of the classes that we actually pass across the interface boundary? Something like that. Less is more. And then last thing, which is, you know, doesn't matter if you don't care about other languages, but to what we do, for example, is very important, is it makes it much, much easier to write bindings to other languages, or at the very least, it gets bindings, it gets people halfway to having the bindings written. We'll see some examples of that. Okay, so I started these slides very late for good reasons, but mostly because I'm a terrible procrastinator. But there are advantages to starting your slides very late, and one of them is getting to know kind of the audience before you actually give the presentation and working that into your slides. And I've noticed one pattern above all at this conference so far, which is people here really like hair polls. So the example library that I'm going to be going through today is called libhairpoll. It's a library for making your own hair-related polls for whatever purposes you might see fit, taking in votes, and then tallying the results up at the end. So this is kind of a slightly boiled down, but more or less accurate version of its header. So all of this is code that I've built and run, no longer than about 2 hours ago, so it probably still builds and runs. And what you can see here is a couple of things. Let's see, does this work? Cursor. Where's my cursor? There we go. All right. So we have this type here called hairpull t. It's just a type def to a pointer of struct hairpull. We can make ourselves one of these, which gives us this guy here, and we can destroy it. I'll get into some of this later. We can add options to it. These are basically like, He-Man or Skeletor or whomever, and a URL for a representative image, because you're going to have to show that to people. People can vote on hairpulls by picking the appropriate option, and we can also tally the results that we've had so far. And basically the way that works is we get called back for each result and informed about it. So there's this ugly type def here as well. Go ahead.
Just a simple comment. You also need to provide the correct conversion in Windows. This interface is insufficient.
Yeah. Well, unless you're happy with the standard, right, which is stdcall, if I remember correctly. Yeah, we'll talk about some of that, but yeah, exactly. I'll get into some issues of visibility and stuff later, and that's actually a very good point. Okay. So, I don't know, maybe you're different from me, but the last slide kind of looked like a whole lot of everything to me. This, to me, looks a lot cleaner. This is something I might actually like to work with. So this is my client-facing, this is the top of the hourglass, what this might look like to an actual client. So we decided, we're going to make this in a class and do this sort of almost OO-ish. We're going to be able to construct one with the name of the person. We're going to be able to add various options to it, vote, and then we're going to get the result back as a list of vectors. Again, no more callbacks or anything like that. We just want a list of vectors at the end. And probably the most interesting part about this is the fact that down here we have just one member, one data member, which is the opaque pointer to the hairpull t. Okay, so that's just kind of a rough introduction. Now I'll go through various aspects of this, talk about some best practices, and kind of explain a few things along the way. And feel free to ask clarifying questions in particular, and maybe the bigger questions at the end. Okay, so the first question you might have is, I'm using C here. You already told me C89, but which parts of C89 should I use? So starting point for me generally for this stuff is C89 plus const. Const, as it turns out, is pretty handy and also has absolutely zero impact on the actual binary interface that's going to be generated. You're not going to get a different function signature or calling convention because of const. And then, of course, / comments, which have absolutely no bearing on your interface, but those are good too. Because, again, this is kind of in my neck of the woods, which is Windows, Linux, Mac for the most part, also Android and iOS. Across at least all of those environments, the compilers today, deal with this stuff just fine. Functions, as you saw, are totally okay. Of course, we're going to need those, but no variadic functions. I'll mention why later. C primitive types are fine, char, void, etc. A few things to keep in mind with the integral types, but I'll talk about those as well. Pointers you can use those to your heart's content. Have pointers to pointers, output parameters through pointers, all that stuff that everybody loves. And now for structs, I'm going to say, okay, if you want to use this pattern, you're only going to forward declare your structs in the C++ terminology. So you're never going to actually give me the body of a struct as part of your header. They're all going to look like that type def you saw earlier for hairpull t, where it's just, struct hairpull t, or struct hairpull, and that's it. And we'll talk about why in a second. Enumerations are fine, but with a caveat. And then function pointers are okay too, as you saw the callback there, totally fine. Sorry, did you have another question?
Method pointers are not
Sorry?
Method pointers on the
Method pointers, yes, well, you mean function pointers? No, because there are no
Non-member function.
Oh, well, there are no such things in C, right? We're already only talking about C here. You know, classes are write out, virtual functions, all that stuff. No, but we're back in 1987 and we haven't met Bjarne yet. So, okay, so let's talk about opaque types. Those are these struct things. Yes.
point that virtual methods are or came long as you single inheritance because they can be represented in C. It's a struct and function pointers.
Well, yeah, a struct of function pointers is fine. A C++ virtual function, not so much, but you know, that's well.
But each compiler does it slightly different.
Yeah, and that's exactly like we're trying to avoid the we're not trying to avoid the patterns that virtual functions allow you to the things that they allow you to do. We're trying to avoid virtual functions themselves as they are implemented by your C++ compiler because it might be a little different from the other C++ compilers if they don't share the same ABI. Okay, so let's talk about opaque types. Like I said, we're going to see this pattern over and over again where we just typedef a completely undeclared, or not, well, mostly undeclared struct to one of these hairpole t's, for example. So note that hairpole t is a pointer. So it's a pointer to one of these struct hairpools. And these struct hairpools, we don't really know what those are yet, but we've got a pointer to them, and we can certainly pass pointers to them into places. And if somebody gives us one of these, somehow they got it, then that's fine. If they give us a pointer to one of these, we can pass it into another function that expects a pointer to one of these, all without ever really knowing what's actually inside of the struct. So here, for example, we have the hairpole vote function. It takes as its first argument which hairpole would you like to vote on, and then which option are you voting for? Hopefully it's He-Man. The way this struct might actually look in terms of its implementation, now this is at the bottom of the hourglass inside of your C++ code that's implementing all of this, is more or less just like this. So we make sure that it's in extern C, it doesn't get name mangled or anything for any of that stuff. Not that it matters too much here, but and then we're just going to stick into it whatever we actually want. And typically, if you follow this pattern, that's going to be some other class that's like it's a class and it has some private stuff and so forth. If it's structish, or if you just don't mind sticking the definition of that stuff right in there, that's fine. But for example, you might not want it to be called hairpole. Maybe you were building a general polling platform, then you came to CppCon and you're like, oh, I'm just going to make this hair-based polling platform now and keep all my internal names the same, but provide a new interface. Those kinds of things happen in real code. So one thing, I think no C++ presentation these days is complete without showing perfect forwarding. So this is perfect forwarding. So if you throw one of these constructors in there, then again, you can construct these the same way that you can construct the actual poll. And I'll move right along before anybody asks me questions about perfect forwarding. So how does that poll look like? Well, it could be anything, right? Like that's just some class that's internal to the library. It could be whatever it needs. When I threw it together today, it's just a pretty bog standard class, but it has public data members and stuff which you might not like. So you could go nuts in here and do whatever you like. The point is this is entirely up to you, and this thing can take all kinds of crazy stuff. It could have virtual functions, all that stuff. That's fine. So those, if you can still remember back when I showed you the libhairpole header, we talked about how, or I showed briefly two functions, construct and destruct, to actually generate one of these. The implementation for these can literally be as simple as this. You might do something a little fancier up here to use a unique pointer until the thing is fully initialized, and then release it when you return it and all that good stuff. But for this simple case, we can just allocate the thing and return a pointer to it. And when we go to destruct it, we delete it. And what we've done here is basically just encapsulate how this class gets allocated, how it gets constructed, all that stuff. The client side doesn't know anything about this. It doesn't know that this is what it's doing. This could be just bumping a shared pointer in the destruct, for example, as well. That would be totally fine. Yeah.
Does part of the Hourglass involve preventing C++EH from crossing the boundary? Because
Yes.
when you return new, that can totally throw.
Yes, I will show, well, I won't show a revised version of that function, but I will talk about error handling in about 3 slides, and we'll get to it then. But that's an excellent question. Yeah, so a lot of the code I'm showing you is kind of trimmed down versions. So you might see slightly more complete versions later on. Okay, so integral types. There's int, short, long, etc. I mean, those are all fine, and you can use short and int and long in your C API if you like, and if you can reasonably assume, which in most cases is probably the case, that it's going to be the same size for your clients, that's not going to be a problem. Chances are, if they're not, you probably have bigger problems. But we'll talk later about other languages a little bit, and when other languages bind into C code, a lot of them say, is this a 32 or a 64-bit integer, because they're not necessarily tied to a particular compiler. Or they are tied to a particular compiler, and then they say, like, here's how you pass an int, and here's how you pass a long, but what they really mean is here's how you pass the kind of int that the language interpreter was compiled with, and so forth. So if you want to be explicit about it, you can just use the std types. They're easy enough to come by these days, and not worry about introducing some subtle difference in there. One point about that is using char, generally fine. You're probably going to want to use char quite a bit, and I've never run into a case myself where this has been a problem. It's more long and long that you might be worried about. Int, you're probably fine on most of, again, in my world of those 5 operating systems as well. Okay, talk about enumerations briefly as you ponder what MOTU stands for. Feel free to, raise your hand if you think you figured it out. So enumerations are fine, but you generally don't, yeah? You got it, that's right. So enumerations are fine, but you generally don't want to pass them as parameters. And again, the reason for this is kind of subtle. Enumerations have a different underlying type depending on potentially which values you actually list in them and so forth. So an enum that uses a 32-bit unsigned type might suddenly become a 64-bit unsigned type if you add a certain value to it, or it might become signed and so forth. So again, your best bet is to kind of say, okay, the enum is really just a way in C to define some constants, right? We're going to more or less ignore the type completely because C pretty much does for the most part anyways. And we're just going to say, what, these values are all 32-bit integers, maybe they're signed, so we're going to make it a signed integer, and that's what you pass down here. You never had really any type safety from doing using an enum there in the first place, so your loss is pretty minimal. And then the other thing that's helpful to do in these interfaces, this is not something I recommend doing in general, but in these interfaces it's helpful to just list out like actual values for each of these. So even though this would have been 0 and 1, if you're looking to sort of minimize brittleness in this API, having the actual values there means if you reorder them in the list or something, they stay exactly the same. And it's another hint for people looking at this interface to say, okay, these numbers are actually part of the interface. It's really the numbers I'm passing in. The enum is almost just documentation. Sorry? Yeah. This is the one piece of code I did not compile, and of course it won't compile. So yeah, either remove the type def or just pretend there's another MOTU alignment at the end. Okay. let's talk about error handling, and we'll get to Stefan's question about exceptions. So there are lots and lots of different ways that you can handle errors in C, and people have their favorites and so forth. This is one that I think happens to work well for these kinds of APIs. It doesn't mean you have to use it. It's just, it works pretty well for the kinds of things I've used this for. And in particular, this one kind of plays nice with C++. We'll see that in a second. So the idea is, rather than returning, for example, an error code or something like that, we take a parameter at the very end. It could be optional or it could be required, but what it is a pointer to a pointer holding the error. So in other words, we allocate an error t somewhere in our client code, which we can do error t as a pointer, right? Not that I've shown its definition here. It's on the next slide. Come on, there we go. So error t is a pointer, okay. And we're going to allocate it on client side. We're going to pass in an address to it, and then the library is going to fill it in if there was an error, and if not, it's just not going to touch it. And like I said, you can make those optional or not. You can do all kinds of stuff. So the implementation of this, again, the interface for this can be as simple as this. So just the opaque struct, a function to actually get something useful out of the error, what happened, get a message maybe, and cleaning up of that error. And there's tricks you can play with trying to sort of get it to not have to be deallocated and stuff, but again, unless you're doing something where you're avoiding allocations altogether, in which case, you can still have this interface, right? So, but the error type is opaque, and if you wanted to, you could add categories, you could add error codes, you could add whatever you like to this, right? Because it's an opaque type, you just define whatever functions you want the clients to be able to use, and that's your errors. So hopefully you're still with me. So the real question is, okay, so I'm not going to be actually writing C code by hand because I like C++ and I want to use it. So how do I maybe say turn this into an exceptions, because I'm one of those people that likes exceptions. Personally, I'm one of those people that's very mixed on exceptions. I seem to like them one day and hate them the next, so I still haven't made up my mind. But if you like exceptions, this is kind of a neat way to turn the errors into exceptions. So, so what we have at the top here, there we go. At the top, we just have a simple sort of RAII class that holds our error. It really doesn't do much more than hold the error, destroy it when it destructs, and initialize it to null, which is important. Down here, we have kind of the magic class. So let me first show you how we might actually use it. So we're writing a C++ member function called vote, or just a free function, whichever. We call hairpole vote, and at the very end, we pass in this throw an error magic. And what that's going to do is, if hairpole vote returns an error through that mechanism, it's actually going to turn into an exception. So let's see how that happens. Sorry. There. So, do I have a mouse cursor? I don't know what happened to my mouse cursor. Apologies. See, this is the terrifying part. It's jumped somewhere completely random. All right. Do it without the magic. So our throw an error class doesn't do a lot either. But what it does do is something that's usually considered really, really bad, which is it throws from a destructor. And don't get me wrong, that is a really bad thing to do. But in this case, it might be excusable. There is one little thing that needs to be kept in mind, but I'll get to that in a second. So the first thing you might note if you're relatively new to C++ 11 is, what's this no except false thing doing there? Well, as of C++ 11, destructors are implicitly, or like by default, assumed to be no except, meaning they guarantee they won't throw exceptions. If they do, they will terminate the program, which as a library is really not a good idea to do to your client, just like terminate them. So we have to actually say, hey, compiler, this destructor will actually throw, and if it does, please allow the exception to propagate rather than calling terminate. Question? Right. I meant to look up the answer to that beforehand. Now, if it does, it's easy enough to fix, right? You just make sure it gets destroyed before you throw, but after you get the message. I honestly don't remember. I don't know if I was hoping Stefan.
It will not leak. The throw-on error has a data member capital error, and the fully constructed data member will be destroyed even if the throw-on error destructor throws. So it's
That was my understanding. So as part of stack unwinding, it'll still get destroyed. And I'm so glad to have Stefan here to answer that question. It's great. So again, this is very simple. What we do is we say, OK, in the destructor, if there's anything in that error, if it's been written to, it's no longer null putter, then throw whatever the message is in there. And then the last piece of magic is that error T star operator, which is what's going to allow us to pass this guy through as a parameter or as an argument to functions that accept an error T star. And it just returns the address saying, like, here, please shove error information into this location. OK, so again, the end result of this, which you only have to write that class once, and it works for all of your functions, is you get to write this, and things get magically turned into exceptions, which is pretty cool. There is one caveat to this I mentioned, which is don't call multiple of these functions with throw-on error in a larger expression, because it turns out the destructor is invoked at the end of the full expression containing its instantiation, and therefore you may not actually have the destructor happen right at the end of the function call. But for these kinds of APIs, most of the time you're actually just, well, actually, I've never encountered a case where I'm not just doing one function call kind of at a time, and it's all buried under C++ code, and then I do more complicated things up above. So it's pretty easy to stick with that rule. If not, you could just not use throw-on error. There's other ways you can do this too. They involve a little bit more boilerplate every time you call a function, but it's all about trade-offs, right? OK, so what about going the other way around? So I'm now at the bottom of the hourglass, and I want to take something that could throw, and I want to turn that exception, if I catch one, into one of these errors. So what you can do this in a bunch of different ways. Let me just jump ahead for a second and show how this is used. So here's a case. It's our good old friend hairpole vote. And in hairpole vote, you give it an option, which actually turns out is behind the scenes an index into a vector. And if it goes out of bounds, we want that to be an error. We don't want that to just crash or do something else bad, undefined. So you could just, in this function write, try, do all this stuff, catch, turn this thing into something else, change out error, all that stuff. And what you will do very soon after that, at least in C++98, is you will write a macro to do the catch block for you, because you are going to be writing it for every single entry point in your shared library. But it turns out in C++ you have lambdas. So you can instead use this cool pattern, which is actually documented in a bunch of different places. I think James has a blog post about it, for example. I've seen at least 2 others. And it's just, this is one of the things that really makes me really like C++. So now we're just going to say, please, in whatever I'm going to do, take any exceptions that might come along and turn them into an error that gets stored in out error. So if I go back, there. If I go back to the implementation of translate exceptions, you can see it's actually pretty simple. It takes anything, a function, presumably, something that's going to have to be callable, because we call it, wraps it in a try-catch block, and if it catches something, it sets up a reasonable error. And this is nice too. So I'm in the habit of deriving my exception classes from std exception, and you probably should be too. But if some other crazy thing gets thrown, if an int gets thrown, or the the C runtime library decides to do something, or C++ runtime library decides to do something interesting where something is signaled through an exception that you can't quite make out its type of, or whatever might happen, at least you can stop it here and you can say, okay, something bad happened, you know, do whatever you need to do, shut me down or something. And it's nice to kind of do this consistently at your interface boundary, so you'll never get an exception leaked across the boundary. Because if you don't do this, despite marking that function extern C, the exception will happily continue to propagate through your quote-unquote C boundary, which even though it's not really, you know, doesn't seem like it should support it, or exceptions should have anything to do with it, it will just, you know, continue to unwind. So that's not a nice thing to do to your clients. Yes?
Is it possible that the pointer returned by what is now pointing at destroyed stuff?
In there?
Yeah. So like.
Error.
String and then
My error actually takes a std string, so it makes a copy of that. Yeah. I'm not sure if I actually show it or not. I don't think I should. But that's a great question. Yeah, sorry, go ahead.
In the cache block, the new statement,
Yeah. Sorry, I couldn't quite.
the new statement in the cache block.
Yeah. Is not ideal, yeah, because it could throw and then bad things would happen. In the kinds of things I do, that's usually not a problem. If it were, again, you would pre-allocate an error somewhere for that case, store your errors in a pool, have just one error that you return at most. You know, lots of ways to deal with that. For me, it's usually not a concern, just because of the kinds of things I'm doing. If I'm out of memory at that point, yeah, exactly. Worse things are going on. But again, yeah, if you care about that kind of code, if you're in that kind of environment, then
Is the reason for pointer-to-pointer for error because you need to pass a pointer through the C binary?
yes. So specifically the reason is error T is what we're treating as the object, sort of the thing. It's our tag, right? And so error T is the thing that we want to change, like that we want to give back. And in order to give something back in C, as other than through the return value, you know, it needs to be a pointer so that we know where to store it. Make sense? Okay. I'm sorry, I should be repeating questions, but I'm not. Yeah.
So it seems that almost your entire function should be inside.
Yes. Yes, it should. Yes, absolutely.
So, okay.
And in this case, it is, right? That first brace there is actually the closing brace from the if. The second to last closing brace is the closing of the lambda. And that's what all of these functions end up looking like. They're all like, do this at the start and then insert code here. And I love lambdas. Okay, so let's talk about callbacks. Callbacks are useful for a variety of things. In our libraries, we use them to tell you when something has happened, like, you know, the presenter just did this, so move along to the next slide. But you know, you could use them for all kinds of things. One of my favorite uses of callbacks is simply to return long lists of things, and instead of worrying about allocating a buffer and then providing some way to iterate through it and stuff, I can just call a C function over and over again and keep providing you with whatever information you would like. So that's what we do here in hairpoll. We have this tally function. It's going to tally up all the results and tell us about it. And so the first thing we have is a function pointer typedef, and it's, you know, ugly as they all are. So I encourage, if you're writing stuff like this, to use typedefs because you will hate yourself if you don't. They make it so much easier because by the time you give it as a parameter, it just looks like anything else. And the other thing I encourage is giving the parameters names, because you can actually do that, and it doesn't really tell the compiler anything at all, but it tells the person who's looking at the code, hey, that's what that parameter is for. It's not just a random char star. So one of the things that is a really, really good idea when you have callbacks is to give your client who's giving you a callback a chance to add some extra information that's going to be passed to that callback. So if you look at this, this callback type, it's back. it takes this client data at the start. And client data is just a void star. It's not an opaque thing or anything like that. It's just a void star. Because we really don't know what it is. It's actually up to the client. So where we call tally, where we pass in the callback function pointer, we also pass in client data, whatever that is. And whatever we get passed here is going to be passed as the first parameter to that function. So in other words, you need to know what context you're in. You need to know, whatever extra data you might need to figure out what's like where were you sort of ultimately called from and what you have. All of that can go through that client data pointer, and really just needs to be the one pointer. So let's look at an example of how that's used. So this is a fun technique to use lambdas as callbacks. And so I apologize, it's kind of small code. It's a lot of code, but it's actually fairly straightforward. So suppose, let's see. All right, well, sorry. So suppose we had a hairpole tally that took a lambda. Maybe it took a sit function of the appropriate signature, or maybe it's templated or something like that. Well, what we would do is probably something like we see at the top here. So first of all, to give you the context, what we're doing here is we're in the results function of hairpole. It's going to call tally. It's going to accumulate all of the results that come through, put them all in a vector, and then return that vector by value, because that's how we do it these days. So if tally took a lambda, you would probably write exactly the top third and bottom third of this, more or less. You just make your lambda. It needs to capture the variable it's going to change, the vector where it's going to push stuff in. It needs to capture that by reference, because we need to actually mutate it. It gets the arguments that the callback is called with, the name, the votes, and in this case, some nice HTML that includes like a link or an image tag to the image of whoever's hair we're looking at. And then it pushes back into ret some internal thing. Maybe it's a struct, maybe it's a class. And again, if tally just took a lambda, that would be it. We would just call tally and pass an add result. But it doesn't. It takes a function pointer and a void pointer. So what do we do? Lambdas that capture cannot be turned just into function pointers willy-nilly. They can be turned into stit functions, but not into function pointers. But luckily, lambdas that don't capture can be turned into function pointers. So what we do is sort of this trampolini kind of thing, where we define a non-capturing lambda called callback. It takes that magic client data parameter, and the first thing it does is cast client data to the type of add result, or more precisely, a pointer to add result. You can't really in C++ name the type of a lambda, but you can decal type it, and you can decal type use that. You can decal type the address of it and so forth. So that's what that decal type there does, is just whatever the type of that lambda is, magic compiler generated stuff that we're not allowed to really know about. Stores that in function. So now it has a pointer. As long as we passed in a pointer to that lambda, add result, it now has a pointer to add result. So it can just dereference the pointer and call it. And that works perfectly hunky-dory fine. And you'll see down here that we do, in fact, pass add result as the parameter right after callback. And therefore, that's what's going to be passed through as client data. So just to remind you, we pass in the handler, and then we pass in the client data from there. OK, so yeah.
In this particular case, you could skip a step by passing essentially add result and pass ret as the void star data. But this technique is good if you need to smuggle an extra.
Well, and what's nice about this is this always works. So this just you can take any lambda.
Turn off your brain and do it.
Yeah, maybe it needs to capture something else by copy or something else by reference. Maybe it, whatever the lambda is, maybe it came from somewhere else. You can essentially pass through any lambda. And so usually I write a little utility function that does exactly this for whichever things take callbacks. It's kind of hard to try and write a general one because it depends on the other parameters and so forth. But you can. Yeah, it just kind of works Yes. Thank you for the heckling. I appreciate it. Moving on. Okay, so I want to talk briefly about symbol visibility. We're almost near the end of the talk. We've got about 10 minutes left of time, so there should be some time for questions. So symbol visibility and linkage and all this stuff. I'm going to kind of gloss over the details because I don't really know them that well, but I know how to use them and make things fast. So in Windows forever, if you've ever written a Windows DLL, you know about declspec, and specifically you know about declspec DLL export and DLL import that are the magic things that I don't quite know what they do, but they make it so that I can call this thing through a DLL, right? And there's two sides to it. When I'm building the library, everything needs to be decorated with DLL export. And when I'm using the library, everything needs to be decorated with DLL import because that's the two sides of that coin. And it turns out in GCC and in Clang and probably a bunch of other compilers, there's this sort of similar related feature around visibility where you can say, hey, I have all these symbols floating around, but really just these few need to be visible. And this can lead to some huge performance improvements in load times for your libraries. If you have millions of symbols, there's this kind of fix-up step that generally has to apply to all of them if they need to be externally accessible. But if they're just kind of internal to the library, then only the ones that actually are actual entry points need to have this. So there's this kind of template for writing this, what I just wrote. This happens to work on Windows, Linux, and Mac with GCC, Clang, and Visual Studio. And if you, for example, Google GCC visibility and you go to the first link, which will be the visibility wiki page on the GCC wiki, you will see code that looks very similar to this. And the main thing there to note is the ifdef hairpole exports near the top there, and that's going to be a macro that we define whenever we build the hairpole library. If you use CMake, a macro like that will be defined for you. So with all that garbage out of the way, you only need to write it once. You can just include the header that's in, or stick it at the front of your header. And now you can dutifully decorate all of your functions with this hairpole export. You'll need to do something like this to get things to work at all on Windows. On Linux, if you then, or Mac, GCC and Clang really, if you then add this magic compiler option to your builds, all the other symbols will become hidden. Only the ones you've explicitly marked will become default visibility. And again, your load times for your library could be a lot faster. Question is back.
As you said, if you're using CMake, there's a function that pretty much does all of that stuff.
But I mean, okay, yeah, that's cool. Oh, I didn't know that. So the comment was just, if you use CMake, there's actually a function that will generate essentially that header for you in addition to it defining the exports variables. Very cool. All right. So almost the last thing, you're writing a header. You're probably going to be mostly including this into C++ code. And if you forget to mark all of your stuff as extern C, you really actually just have a bunch of C++ functions or interfaces lying around. So you haven't saved yourself a whole lot of anything. And if you ever try to build a C client and then link it to the C++ library that you've built, you would find that there's all these undefined symbols, and you'd go, why the heck is that? So remember to stick this stuff around your header. And generally in the implementation as well, and you'll be fine. Okay, so I want to briefly talk about lifetime and ownership, and then onto something completely different, and then we'll finish up. So, I mean, this is much like I see lifetime and ownership in C++ in general these days, where the answer is often just use unique pointer, like just don't do anything else, just use unique pointer. If you really have to, use shared pointer, but mostly just use unique pointer. So first of all, that construct destruct that's basically, poor man's unique pointer is really just new and delete. So you definitely want to wrap that in an RAII class so that all of that is taken care of for you, because RAII is one of the best C++ features, or idioms rather, in existence. the other thing is, if you need to do ref counting, I've written libraries where I actually like expose reference counts, and I have like increment and decrement and all that stuff. But if you do this, you can just treat that one owner thing, that one destruct construct, as essentially a reference count increment and reference count decrement. So where internally, right, you might have a shared pitter, for example, that you're actually decrement or getting rid of when it's doing destruct. And so if the library needs to internally keep some object alive still for whatever reason, it can still continue to do so. And then the same thing goes above the hourglass at the top. On the client side, if you need to ref count some resource, well, just ref count the resource that was given to you, right? There's no need to really build ref counting into the API. There might be performance reasons for doing so, but I kind of doubt it. One really nice thing is whenever you're calling a callback, it's part of this, like it's on the stack. So whatever data you give to it can actually live on the stack. And so for sort of short-lived data that you're passing through, that's really nice because you can just pass the data through, the callback can consume it, hopefully make a copy of it or do whatever it does because it's about to go away. And when the callback returns, then you can clear it off the stack. Okay, so briefly, I know this is CppCon, but I did want to talk about those other languages. So I have clients that use next to everything under the sun. And I have internal clients that use interesting environments like MATLAB. And all of these things, they want to use this stuff from everything. It's crazy. So how do you do that? Well, it turns out there's this thing called foreign function interfaces. Really, all that is something that lets you, given code written in one language, call it from another language. That's it. Very simple. But it has a fancy name, and people like to use the fancy name. C is essentially the de facto standard for foreign function interfaces in terms of the thing that you can call, right? Every language under the sun that's actually out there in real use that isn't like constructed purely for making people's lives miserable, like malbolge, for example. All the real languages, and some of the not real ones too, have support for calling C functions. I've listed a bunch there, but I don't need to go through them. One thing to note is there's a great library called libFFI that takes care of a lot of the sort of details of marshalling and so forth for that. Now the nice thing is, so they have FFI support, and they all support some like subset of C that they can call into, right? Some of them can call functions that take structs by value. Some of them can't. It's just how it is. It's a reality. If you follow all of the best practices mentioned earlier, your library will be callable from basically any language out there. And so the way this might look in Python, for example, so that, again, this is running code. I had this running earlier. I haven't shown you a little bit of preamble, but you can like just basically call C functions. This isn't how I would expose this in Python. I would make a nice Pythonic interface that like probably has classes and all kinds of stuff. But this works, and on top of this, you can build whatever wonderful language-specific interface that you want. Our JavaScript interface is like crazy. It does things that I don't understand, but they're pretty neat. So and you'll notice that, for example, we're passing in a Python function to be called as the callback, and all this stuff works. Like it seems kind of crazy, but it all just works. Now to actually do this, you'd need some preamble. So this slide plus the previous slide is a complete Python program that will execute if you have that library. I was doing this on my Mac, so it's got a .dylib extension, but essentially that's how it works. You say load this library, and then you can just call into it. With C types in particular, you can actually make calls without ever telling C types this is the signature of these functions, and it'll just try to guess. It generally doesn't do a great job of guessing in my experience, so this is all just code basically telling it, hey, this function takes this return type and these argument types. That's it. But the Node.js code for this, there's a module called FFI, would look almost identical. It turns out in MATLAB, you can do crazy things to call C functions and do kind of the same thing. In Java, you have to like build JNI, which is kind of gross, but you would have to do that no matter what. But in a lot of languages, you can just sort of say, here's a C function, call it, please. Okay, so I'll finish up. I'm slightly over time. So Hourglass, basically, what is it? It's really just C++ on top of C89 on top of C++ with some restrictions, and maybe the top isn't always C++. We can avoid various ABI issues, very sneaky dependencies into our interface, and again, still have the full flexibility of using all these things above and below, but just not have them actually impact whether our library works on a given day of the week. It hides the object layout of everything and all kinds of other implementation details, which makes it much easier to ship bug fixes, for example. And it makes FFI bindings easy. So if you don't want your shared library experience to look like this, use Hourglass, and maybe it'll look more like this. That's it. All right, questions?
Couple of things. How does this compare to Swig?
So that's a great question. I was hoping somebody would ask. So Swig, and the question's well, you heard the question. Swig is this tool that slurps in code. I don't know what all it can slurp in, but it can definitely slurp in C++ code. And it will generate sort of an FFI library for you for whichever targets you specify. And it supports a pretty impressive array of languages, but not all of them. It doesn't do JavaScript, for example. And it's a really cool project, but there's kind of two issues I have with Swig. So one is that it breaks on certain things. So you can't just take a C++ code base that's like uses absolutely everything under the sun and say, here Swig, make this magically for some other language. Like writing C++ front ends is hard, and Swig is not a complete C++ front end, at least not the last time I used it. The other thing, the code that it generates on the other end is kind of, it's an attempt to mirror whatever is there in C or C++ in that language. So you get an interface similar to the C-types one that I showed you in Python if you give it a bunch of C functions. You're going to essentially get a bunch of C functions out the other end. If you do something like this, which there's lots of reasons to do, that's the easy part, right? You write that in like an hour and you're done and you basically never touch it. It would be nice to maybe automate some of it, and I have an interest in doing so. But if you've kept your interface simple, doing the work of Swig is the easy part. To me, the more interesting part of targeting languages is finding ways to express the same semantics with those languages' native idioms and however you do things over there. So
Is it fair then to say that if you use Swig to generate a C library, if it works for it, then the Pythonic are hopefully not the MATLABic version of the I'm brain damaged by having to work with MATLAB for 20 years. So I agree that's a separate thing, right? So can this be split into two pieces?
Well, what you could do is you could run Swig on the C library that you have there, and again, because you've used so few features, it will work. Like Swig will, I don't think, ever choke on code that follows those conventions. Yeah, and so that might be a good way to get that low-level library, but you're still going to have to do, again, your own work to make it nice in that language.
You're also, like in my experience anyway, with Swig, you're going to have to do some work to get Swig to only Swig the parts of your library that you care about in a way that's actually usable on the other side. Yeah, so the comment is you might have to tell Swig in very arcane ways to only Swig these parts of your code, and again, if your entire library interface is in one header, and it's all C code, you can just point Swig at that header, and you're done.
Could you say just a little bit more about returning a shared pointer from the C create function?
Okay, so when you remember that struct, let's go way back. No, this is not where I should want. Here, let me just jump right there. So way back here, we had that struct, right? So imagine if that struct contained a shared putter to pull. Now I could have other shared putters to pull all over my code. Once the client is done with it, it's going to call destruct. That shared putter will get destructed. The reference count will drop. May or may not be destructed at that point. And the same thing kind of applies in reverse on top. If I get a hair pull T out, I can put that in a shared putter at the top, and when it goes down to 0, it can just call destruct, and everything's good. Okay, any other last questions?
I have a brief comment. Tomorrow, Dropbox is releasing an open source library to do these kind of things, but specific for mobile. So Objective-C and JNI.
Oh, awesome.
Doing this for C is like awesome. Doing it for JNI is like just banging your head against a wall. So if you're curious about details of that, come to the talk on Thursday. But
very good
stuff, just not for Python, JavaScript, MATLAB. God help you.
Very cool. Awesome. Thanks. Okay. If there's no other questions, I think we'll wrap up. So thanks a lot for attending, and really appreciate it.